There's a star cluster in the constellation Scorpius that almost every amateur astronomer has seen. It sits about 1.5 degrees from Antares, close enough that both fit in the same low-power field of view, Messier 4. It is the nearest globular cluster to Earth, roughly 6,000 light-years away, a loose swarm of something like 100,000 very old stars. It has been catalogued, sketched, photographed, and studied for more than 250 years. In August of 2026, a team of astronomers published a paper that put Messier 4 on a list of 12 objects. The list had one organizing idea behind it, and it was not a comfortable one. None of those 12 clusters, the authors argued, were born in the Milky Way. They were born somewhere else, in another galaxy, a galaxy that no longer exists because ours ate it. That claim by itself is not new. Astronomers have known for years that the Milky Way is partly built out of the corpses of smaller galaxies. What made this particular list matter was the date attached to it, and the way that date was obtained. Because the 12 clusters did not come from the last major collision our galaxy experienced. They came from something older, something that happened when the universe itself was still in its opening act, and the Milky Way was not yet the Milky Way. To understand why that was so difficult to prove, and why it stayed unproven for the better part of a decade, you have to understand what happens to evidence in the center of a galaxy. Our galaxy today is a spiral roughly 100,000 light-years across, holding a few 100 billion stars. It did not start that way. It grew, and it grew through two processes running in parallel. Some of its stars condensed out of gas that already belonged to it. The rest arrived as immigrants pulled in when smaller galaxies wandered too close, were torn apart by tides, and had their stars, gas, and dark matter folded into the larger system. We can watch the most recent example happening right now. The Sagittarius dwarf galaxy fell toward us more than 6 billion years ago and is still being dismantled, its stars smeared into long streams that wrap around the sky. Before that, around 10 billion years ago, the Milky Way collided with something considerably bigger, a dwarf galaxy now called Gaia-Sausage-Enceladus. That event was identified in 2018, and it changed how astronomers think about our galaxy's structure. The mass ratio was somewhere around 1 to 4 or 1 to 5. When a galaxy takes a hit like that, the disk it already has gets stirred and thickened, and a burst of new star formation follows. The thick disk we live near the edge of today is, in large part, a scar from that impact. So the sequence looked reasonably tidy. Sagittarius, 6 billion years ago and ongoing. Gaia-Sausage-Enceladus, 10 billion years ago. A scattering of smaller events in between, and then, before 10 billion years ago, a wall. The problem is not that nothing happened back there. The problem is that our tools stop working. Two things go wrong at once, and they compound each other. The first is a matter of proportion. 12 billion years ago, the Milky Way was not a giant surrounded by dwarfs. It was small. The galaxies falling into it were comparable in size to what it already was. When a big galaxy swallows a tiny one, the tiny one's stars keep an obvious signature. Unusual orbits, a distinct chemical fingerprint, a sense of not belonging. When two roughly equal objects merge, that distinction blurs. Both were young. Both were chemically primitive. Both were forming stars quickly. Their debris ends up looking like the same thing. The second problem is worse, and it is specific to the region where this evidence is buried. Debris from the earliest mergers should be concentrated in the innermost few thousand light-years of the galaxy, sunk deep into the middle by gravity. But the inner Milky Way contains a rotating bar of stars, and that bar acts on orbits in a way that is technically chaotic. Over 10 billion years, it scrambles them. The neat orbital signature that would let you say these stars all arrived together gets erased. The galaxy destroys its own records. This is why, for years, the early history of the Milky Way was less a body of knowledge than a running argument. There were candidates. In 2019, a group at Groningen sorted the Milky Way's globular clusters by orbital properties and noticed a set of about 20 that clustered together at unusually low orbital energy, sitting close to the galactic center, and that did not match any known merger. They called it, plainly, the low-energy group and suggested it might be the wreckage of some unidentified accretion event. That same year, a separate team working from cosmological simulations came at the problem from the other direction. They counted how many globular clusters the Milky Way has whose origin nobody could account for, compared that number to what simulated galaxies produce, and concluded that our galaxy must have swallowed a substantial object early on. They named the hypothetical galaxy Kraken. Then, in 2021, a third line of evidence appeared. A survey of stellar chemistry in the inner galaxy turned up a population of stars that were metal-poor and chemically unevolved. Stars that had formed before much cosmic enrichment had taken place, and that seemed out of place where they were sitting. That population was named Heracles. 3 names, 3 methods, 3 teams, and no way to know whether they were describing one galaxy, 3 galaxies, or nothing at all, because every one of those results was attacked, and the attacks were not unreasonable. The chemical argument for Heracles depended on abundance ratios that, it turned out, do not cleanly separate accreted stars from homegrown ones once you get to very low metallicity. The orbital argument for the low-energy group ran straight into the bar problem. If the bar scrambles orbits, a tight orbital grouping might be a coincidence rather than a family, and several papers pushed back hard, arguing from the aluminum content of those clusters that they had formed inside the Milky Way all along, no external galaxy required. By the middle of the 2020s, the field had a genuine impasse. Simulations said early mergers should have happened. Observations offered suggestive hints. Nobody could produce a measurement that settled it. What was missing was not a better telescope. It was a clock. Here's the idea that broke the problem open, and it is worth slowing down for, because everything downstream depends on it. Galaxies enrich themselves over time. The first stars form from hydrogen and helium and almost nothing else. When those stars die, they seed their surroundings with heavier elements: carbon, oxygen, magnesium, iron. The next generation forms out of that enriched material, so it starts with a higher metal content. Repeat this for a few billion years, and you get a relationship. In any given galaxy, the older a star is, the fewer heavy elements it contains. Astronomers call that the age-metallicity relation. The crucial part is that the relation is not universal. Its shape depends on the galaxy. A massive galaxy holds onto its enriched gas, forms stars rapidly, and climbs to high metal content fast. A small dwarf galaxy, with weaker gravity, loses much of its enriched material to outflows and enriches slowly. So a dwarf in a large galaxy of exactly the same age will contain stars with measurably different metal content, which means the age-metallicity relation is not just a curve. It is a signature of origin. If you can plot enough objects on that graph with enough precision, stars born in different galaxies should fall along different tracks, and the tracks should stay, separated even in the metal-poor regime where chemistry alone gives up. But you cannot do this with individual stars. Determining the age of one star to better than 1 billion years is close to impossible. You need objects where every member formed at essentially the same moment out of the same material. You need star clusters, which brings us back to Messier 4 and to a telescope that has been in orbit since 1990. Globular clusters are unusually good witnesses, for a reason that has to do with gravity. A loose association of stars drifting through a galaxy gets pulled apart within a few 100 million years. Tidal forces from passing gas clouds and from the galaxy itself are simply stronger than the association's own weak self-gravity. A globular cluster is different. Tens of thousands to a few million stars packed into a sphere a few dozen light years across is dense enough to hold itself together against those forces for the entire age of the universe. When a dwarf galaxy is destroyed, its diffuse stars disperse into the halo and lose their identity almost immediately. Its globular clusters survive the wreck intact, still bound, still carrying the chemistry of the gas they condensed from in a galaxy that no longer exists. They are, in the most literal sense, artifacts that outlived their civilization. The technique is old and elegant. Plot every star in a cluster by brightness against color, and you get a distinctive shape. Stars burn hydrogen along a diagonal band, and they leave that band when they exhaust the hydrogen in their cores. Heavier stars run out sooner. So the point where the band bends away, the turnoff, creeps steadily downward as a cluster ages, like a waterline dropping in a reservoir. Find the turnoff, and you have the age. In practice, this is where the whole enterprise usually falls apart. The turnoff point is subtle, in a small error in the cluster's distance, or in how much interstellar dust reddens its light, or in which theoretical stellar models you use translates into an age error of 1 billion years or more. Worse, different research groups made those choices differently. Compiling ages from the literature meant compiling everyone's incompatible systematic errors along with them. That, more than anything else, is why the age-metallicity approach had never resolved the argument. The measurements were not sharp, enough to separate tracks that sit only a few 100 million years apart. The team behind the 2026 result, led by Davide Massari at the Astrophysics Observatory in Bologna, attacked that problem rather than the astronomical one. Their project carries the name CARMA, Cluster Ages to Reconstruct the Milky Way Assembly, and its governing rule is brutal consistency. Every cluster measured with Hubble imaging in the same 2 filters, every image corrected for dust that varies from one side of a cluster to the other, every field star that happens to lie along the line of sight identified by its motion across the sky and thrown out, so the diagram contains only genuine cluster members. Every cluster fit against the same family of stellar models, with age, distance, metallicity, and reddening all left free to float rather than fixed to some prior assumption. Much of the raw imaging was not new. It came from Hubble's archive, from surveys of globular clusters that had been observed years earlier for other reasons, plus a program specifically targeting clusters that earlier surveys had skipped. This is a point worth pausing on. Hubble did not point at anything to make this discovery. The photons had already arrived. They had been sitting in a data archive in Baltimore, and what changed was the analysis. The result was precision on a different scale entirely. Where a well-regarded earlier catalog achieved average age uncertainties near 900 million years, this method reached about 260 million, roughly 3.5 times sharper. For the first time, the gaps between tracks were larger than the error bars. They applied it to 17 clusters in the inner galaxy that had never been measured this way, 15 of them from the disputed low-energy group, and combined those with earlier karma, results for a total of 39 clusters, all on one homogeneous scale, concentrated inside about 20,000 light-years of the galactic center. Then they did something important, which was to avoid deciding the answer in advance. Rather than sorting clusters into groups by eye, they built a statistical model in which the number of parent galaxies was itself an unknown to be determined by the data. Each hypothetical parent would follow its own age metallicity track and its own orbital signature. The model was run assuming 2 parents, then 3, then 4, and the versions were compared by how, well, each accounted for the observations. The expectation was 2, clusters born in the Milky Way and clusters delivered by Gaia-Sausage-Enceladus. That is what the known history predicted. 2 was decisively rejected. 4 was not favored either. 3 won. There was a population sitting between the other 2 on the age metallicity plane, following a track of its own, separated from the clusters born in the Milky Way, separated from the clusters brought in by Gaia-Sausage-Enceladus, and separated at every metallicity, not just in one narrow range. 12 clusters, all of them confined to the inner 20,000 light-years. 10 of the 12 came from the old low-energy group. Those clusters could not have formed in our galaxy, and they had not arrived with the merger we already knew about. They came from a third place. The authors gave that third place a name, Low-energy-Kraken-Heracles, LKH, deliberately combining all 3 earlier candidates in one label. Not out of politeness. The point of the name is the finding. The low-energy group, the predicted Kraken, and the chemically odd Heracles stars were not 3 separate mysteries. They were partial views of one object, seen through 3. Imperfect instruments. It is also a correction, and the field has needed corrections before. When the Kraken hypothesis was first proposed, it rested on a list of clusters sorted into 3 supposed merger events. One of those events was an object called Canis Major, an apparent overdensity of stars in the outer disk that had been interpreted as a captured dwarf galaxy. Canis Major turned out not to exist. The overdensity was a warp in the Milky Way's own disk, seen at an unfortunate angle, and most of the clusters assigned to it actually belonged to Gaia-Sausage-Enceladus. That history is a reminder of how easily a pattern in the data can be read as a galaxy, and it is exactly why the 2026 analysis was built to let the number of parent galaxies emerge from the statistics rather than be assumed. So what was LKH? Fitting a chemical evolution model to the LKH track gives a stellar mass of roughly 500 million times the mass of the Sun. That is small by our standards, under 1% of the Milky Way's stellar mass today, but it is almost exactly the mass estimated for Gaia-Sausage-Enceladus, the collision that built our thick disk. And the comparison that matters is not with the Milky Way now. It is with the Milky Way then. 12 billion years ago, our galaxy was a fraction of its current size, and a 500 million solar mass intruder was not a minor visitor. It was a substantial fraction of everything that was there. The same fit gives the timing. LKH was absorbed about 1.8 billion years before Gaia-Sausage-Enceladus. That number, 1.8 billion years, is the robust one, and it is worth being precise about why. The method measures ages relative to one another far better than it measures them on an absolute scale, because absolute ages depend on which set of theoretical stellar models you trust. The team is explicit about this. Some of their raw fitted ages come out slightly older than the age of the universe, which sounds alarming until you realize it is a known offset in the model scale and cancels out entirely when you compare clusters to each other. The gap between the tracks is real and sharply measured. Converting that gap to a calendar date requires anchoring it to something. Anchor it to Gaia-Sausage-Enceladus at 10 billion years, and LKH lands around 11.8 billion years ago, roughly 2 billion years after the Big Bang. Anchor it to a more recent estimate of 10.5 billion, and LKH moves back to about 12.3 billion years ago, a redshift above 4, less than a billion, and a half years after the Big Bang. That range is the honest answer. The event is nailed down relative to the rest of our galaxy's history. Its exact position on the cosmic calendar depends on a reference point that is still being refined. Either way, it is by far the earliest event in the Milky Way's assembly to be identified from direct evidence rather than inferred from simulations. It pushes the documented history of our galaxy nearly 2 billion years further back than anything before it. Which raises the obvious objection: what about the aluminum? Several groups had argued that these very clusters showed chemical signatures pointing to a homegrown origin. The new analysis addresses that directly, and the answer is that the diagnostic itself does not hold up. Clusters that unambiguously came in with Gaia-Sausage-Enceladus show the same aluminum enhancement in their first generation of stars, so do metal-poor clusters in the Large Magellanic Cloud, which is indisputably a separate galaxy. If a supposedly discriminating chemical marker appears in objects known to be foreign, it cannot be used to prove that something is native. The test was not measuring what it was assumed to measure. There is also a broader consistency check. Cosmological simulations of galaxies like ours typically predict between 1 and 4 significant mergers over a lifetime. When the researchers examined simulated Milky Way analogs, several produced exactly the pattern found in the real data. 3 distinct age metallicity tracks, separated by a few hundred million years at any given metal content, corresponding to the main progenitor, a Gaia-Sausage-Enceladus-like event, and an earlier massive one. The observation had a theoretical shape waiting for it. What this changes is the story of our galaxy's childhood. One account of the early Milky Way holds that its innermost oldest stars formed in place, in a chaotic proto-galaxy building itself from its own gas. The new result does not erase that population, but it makes it insufficient. A galaxy carrying 500 million solar masses of stars, plus gas and dark matter that Hubble cannot see, and this method cannot weigh, fell in and deposited most of its material within the inner 6,000 parsecs. As Massari put it, the paper identifies where the first significant batch of bricks came from. That mass would have shaped the gravitational well in which everything afterward assembled. The bulge, the thick disk, the earliest structures of our galaxy all formed in a potential that LKH helped dig. The old stars in the heart of the Milky Way are, in part, immigrants, and they arrived before the galaxy had a proper shape to arrive into. Considerable uncertainty remains, and the authors do not hide it. The technique only detects progenitors massive enough to have carried their own globular clusters, which means smaller galaxies that fell in around the same time are invisible to it. And the early universe was full of small galaxies. The paper's own phrasing is careful. The third track corresponds to at least one merger. Whether LKH was a single dwarf galaxy or the combined debris of 2 or 3 arriving close together is not resolved by this data. The mass estimate carries wide error bars, and the absolute date, as we have seen, moves with its anchor. Some of this will yield to work already underway. The team is continuing to measure clusters in Hubble's archive that have never been analyzed at this precision, which will populate the tracks more densely and test whether the middle sequence is really one sequence or 2 overlapping ones. Beyond that, missions designed to determine stellar ages through astrosismology, reading the ages of individual stars from the way they oscillate, could eventually provide the same chronological leverage for millions of stars rather than dozens of clusters. If that works, the first billion years of the Milky Way stops being a wall and becomes a timeline. But step back from the machinery for a moment and consider what actually happened here. A galaxy formed in the early universe. It made stars, and among them a set of dense clusters. It never became large. Well before the Sun, it existed. Before the Earth existed. Before our galaxy had a disk worth the name, it fell into a young Milky Way and was pulled apart. Everything it had ever made was scattered and mixed into a larger system that kept growing. It left no image, no remnant, no visible boundary. On any photograph of the inner galaxy, its stars sit indistinguishably among ours. And yet it left a clock. 12 dense knots of stars, each one holding the exact chemical composition of the gas it condensed from, and each one carrying the moment of its own birth encoded in the shape of a curve on a diagram. Those clusters had been observed for centuries and imaged by Hubble years ago. The information was already in hand. It took a method precise enough to read a difference of a few 100 million years across a span of 12 billion for the pattern to separate out of the noise. Messier 4 is still there, a degree and a half from Antares, a smudge in a small telescope on a summer night. It has not changed. What has changed is that we can now say with reasonable confidence that it did not start here, and that it is one of the last surviving fragments of the first thing our galaxy ever devoured. If this documentary was worth your time, subscribing helps more people find it.